Hello dear students, welcome back to my channel. Now we are discussing Kohlrausch's law of independent migration of ions. So it is lecture 9. I have completed up to Debye-Onsager equation. So this is the next lecture, continuation for that. If anybody not watched those, just watch. So it will be more clear. Let's start our today's topic. Kohlrausch's law of independent migration of ions. So why we have to study this? Just before going to that, let's see why does weak electrolyte molar conductivity increases so sharply on dilution, and why we can calculate the molar conductivity of acetic acid even though it doesn't fully dissociate. It's not about acetic acid for any weak electrolyte. So the answer lies in one powerful concept called as Kohlrausch's law of independent migration of ions. He studied electrical conductance of electrolytes. In the year of 1875, he observed something interesting, that at infinite dilution, each ion contributes independently to the total conductivity of solution. So this became known as Kohlrausch's law now. Exactly can define Kohlrausch's law we can discuss here. At infinite dilution, so if you add too much water to the electrolyte, what happens? Each ion contributes a definite value to the molar conductivity of an electrolyte. And independent of the nature of other ion present. Like it is independent of the other ion. Every ion is responsible, or it contributes certain conductivity value. That's nothing but Kohlrausch's law. So to understand better, you can see with the example. If an electrolyte dissociated to A plus and B minus, the molar conductivity at infinite dilution, lambda naught equals to lambda naught plus lambda naught minus. So here lambda naught. So if you take example like CH3COOH, lambda naught M, you can write it as lambda naught CH3COO minus and lambda naught CH plus. This is how we can represent what happens when we add more water or at infinite dilution. Exactly why the weak electrolyte conductance sharply increases over dilution. That's what we are discussing here. At infinite dilution, infinite means too much water if you add, or solvent. At infinite dilution, what happens is ions are very far apart, means ions will move away from each other so that attractions will be less between them, which means no interactions. If no attractions or interactions, the ions moves with high velocity. No interactions, so each ion moves independently. So ion movement itself, the conductivity. So what we can conclude from this, conductivity becomes the sum of individual ionic contributions. So in simple words, if you ask, just every ion responsible for the finding conductivity of weak electrolyte over infinite dilution. That's nothing but Kohlrausch's law. And coming to applications of Kohlrausch's law, most important this only. Mostly questions are from in this area. So the first one is use it to calculate the molar conductivity of weak electrolyte. Weak electrolyte. Just this is the first application. What is it? We can see. We want to find lambda naught m CH3COOH. What we can do? Lambda naught of CH3COO minus and lambda naught of CH plus. This is the basic one. Suppose if they give equation, ask what is the lambda naught m CH3COOH by giving other electrolyte values. So what is it? Just you take example of CH3COOH plus NaCl gives rise to CH3COO plus HCl. So we need to find lambda m naught value for this. How do we calculate? So lambda m naught value of CH3COOH equals to, here lambda m naught value of reactant sum is equals to the lambda m naught value of product sum. So that's why what we can write, lambda naught CH3COO Na plus lambda naught of HCl plus minus lambda naught of NaCl. This is how we can calculate the lambda m naught of weak electrolyte. Whatever they give, just you have to make equation and you have to write it. Suppose we have also discussed one of the important relation between lambda m naught equals to lambda naught EQ into n factor. This is the relation. With this relation also questions possible to ask. Coming to second application, we'll discuss in questions all these applications. So second application is degree of dissociation, which is nothing but DOD or alpha. Degree of dissociation indicated as like this. The symbol is alpha. So alpha equals to lambda m by lambda naught m. What is that? It is the ratio of lambda m to lambda naught m. This is just molar conductivity at any concentration. It is same molar conductivity at infinite dilution. So generally this is more value than this, so that alpha value is less than 1. The over dilution, the conductivity increasing for the weak electrolyte sharply. That's what Kohlrausch's law. Why it is increasing sharply, explained by Kohlrausch's law. Means every ion contribution increases the molar conductivity of weak electrolyte over infinite dilution. So this is the second application. Here lambda m and lambda naught m directly won't give. Lambda m naught can calculated from the previous application. Lambda you can calculate it with this formula which we discussed in the previous lecture. If anybody not watched, just watch that. Surely you will understand this better. K into 1000 by molarity. So this is how they may give lambda m value. Like kappa means conductance, specific conductance or conductivity. Kappa is specific conductance or conductivity. And this is molarity and 1000. So degree of dissociation, this is the formula. Degree of dissociation is just like number of moles of reactant or number of moles of electrolyte dissociated to number of moles of electrolyte taken initially. So similarly dissociation constant dissociation constant is Ka value. So Ka equals to C alpha square by 1 minus alpha. How do we calculate this one? This we did in the Oswald dilution law, because that is also related to weak electrolyte. So you can take example of weak acid as HA. It's split into H plus and A minus, and initial concentration of weak electrolyte is C. Product concentration initially 0. So at time t equals to 0. So at time is 0. So when time becomes t seconds, then some of the product is formed, that we are writing it as alpha. Since it is from C, we are writing C alpha, and this can take it as C minus C alpha, that I can write it as C into 1 minus alpha. So Ka we can write it as Ka equals to, this is the final formula how we get, that we are doing here. So Ka equals to H plus product by reactant acidic constant or equilibrium constant by HA. So this we can write it as, so at time t, C alpha into C alpha by C into 1 minus alpha, which can be written as C square alpha square by, C square alpha square by C into 1 minus alpha. So here C gets cancelled, then C alpha square by 1 minus alpha. This is the formula for Ka value. But in case of weak electrolytes, or the alpha, if it is very less, that's around 10 power minus 3, if it is less than this, we'll take alpha is negligible. That's why we can write Ka always C alpha square by 1, which can be written as Ka equals to C alpha square only. So but here if you want alpha, what you can write, Ka by C under root. So here C is nothing but N by V. Suppose V is, N, if you take 1 mole, then what is the result? Alpha equals to under root Ka into V. And here they asked H plus, right? From the equation, if you take H plus is here, you can see H plus is this one. So H plus equals to C alpha, right? So H equals to C we can write as it is, and alpha is Ka by C. This formula I can write it first. So if I write like this, then what is the resultant equation? H plus equals to C, if I send inside, I can get C square into Ka by C, which can be written as under root Ka into C. This is the H plus formula. Now, because if you know H plus, you can write negative log of H plus, right, for finding pH. So H plus equals to negative log of, pH equals to negative log of H plus with base 10. So negative log of H plus, the place of H plus I can write this one. So under root Ka C. So this under root I can write it as Ka into C power half. So this, if you simplify, what I am going to get is, that is very important formula that you studied in Oswald dilution law. So just the formula for this, half into pKa minus log C. This is the formula for finding pH of weak electrolyte. That means here there is an option to ask questions with equilibrium concepts. So coming to next, it is used to calculate KSP also. So application for, let's see the Next application, calculation of solubility and KSP for any sparingly soluble salt. For any sparingly soluble salt means partially soluble salt. Soluble salt. Just take AgCl or BaSO4. So it's soluble partially in water. For them, how do we calculate KSP value? Lambda m equals to K into 1000 by. In the place of molarity, we can take solubility for this kind of electrolytes. So you will get lambda m can be written as lambda m naught. Lambda m naught equals to K into 1000 by molarity or solubility. So what we can conclude? Solubility can write it as K into 1000 by lambda m naught. So this is how we can get solubility. This is how you can get S. So that can be used to find KSP. Suppose if you take AgCl, Ag plus and Cl minus. So S into S. So KSP equals to S power 1 and S power 1, which can be written as S power 2. So under root KSP equals to S. This is how we can get some important points. Very important. Here we can add additional points. Ionic conductance. Can write it as lambda. And mobility of ions is U. In any electrolytic solution, the ionic conductance of any ion is directly proportional to their mobility or speed of the ion. So lambda I can write it as nu, because ionic conductance is directly proportional to nu. It's for cation and anion both. So what we can write it is lambda c, we can write it as Faraday into mobility of ion for cation. Same way for anion, F into UA. So that's how we can make the relation between lambda and U. And similarly, one more, transport number, because these two decide molar conductivity of the electrolyte at infinite dilution. Transport number, we can also call it as Hittorf's number. Hittorf's number. So what this explains? Just the current flowing through an electrolytic solution is carried by ions, either cations or anions. So the fraction of total charge carried by any ion is called as transport number. The fraction of total charge carried by an ion is called transport number. So transport number, you can write it as T, cation means Tc, lambda c by lambda c plus lambda a, which can be written as Uc by Ua plus Uc. This is nothing but transport number for cation. And same way transport number for anion, lambda a by lambda c plus lambda a, which is equals to Ua by Uc plus Ua. And always sum of transport of cation and anion equals to 1. Tc plus Ta equals to 1. When Uc equals to Ua, then Tc equals to Ta, which is equals to 0.5. So these are the additional points related to electrolytic conductance of weak electrolyte. Hope it is clear until this. So next we are going to discuss problems related to this Kohlraush's law. Those are very important. Must watch